Welcome to GenAI Research Insight Hub. In today's video, we're exploring the 150-year journey of OCR, Optical Character Recognition, and trust me, this is one of the most fascinating stories in AI history. Let's start our journey from the very beginning. Early OCR, reading by template matching. Inventors attempted to build an artificial eye using photocells and mechanical templates. They used light sensors to detect dark versus light shapes. 1870, C.R. Carey created a mechanical retina. This device sensed patterns but didn't truly understand letters. 1914, Emanuel Goldberg converted printed characters into telegraph code, a major milestone. Early machine reading system. 1954, David Shepard, first commercial OCR using template matching. The machine compared each letter with stored perfect shapes. The diagram shows an input letter A being compared with multiple templates. Only the exact match is selected, while all slightly different shapes are rejected. This explains why early OCR worked only for one font and perfect print. The rule-based approach to OCR. Engineers wrote rules to describe letters using geometric features. Instead of templates, machines used shapes and properties. Features included holes, lines, curves, strokes, endpoints, junctions. Each character was broken down into these simple parts. Example rule: one loop plus one vertical line, likely P. Letters were recognized using these logic-based formulas. 1974, Kurzweil OCR recognized multiple fonts, a huge improvement over single-font OCR. The diagram compares the old pixel matching method with the new feature-based method. In the new system, the letter A is broken into diagonal lines and junctions. This allowed OCR to handle more fonts and shapes. Why rule-based OCR failed? Real-world text varies: degraded scans, touching letters, new fonts, smudges. Hard to write rules for all messy situations. Engineers added more rules for each problem. The system grew complicated and harder to maintain. Rules collided and created thousands of exceptions. The system became unstable and unpredictable. Eventually became a house of cards system. Changing one rule would break many others. The diagram shows a fragile card tower labeled with different rules. It represents how each new rule weakened the whole system. A small variation in text could collapse the OCR engine completely. The diagram shows a fragile card tower labeled with different rules. It represents how each new rule weakened the whole system. A small variation in text could collapse the OCR engine completely. Machines start learning patterns, stop giving rules. Let machines learn from examples. OCR shifted from logic to data-driven learning. OCR identified statistical patterns in pixel distributions. Machines learned what typical letters look like. Hidden Markov models treated reading as sequential probability. Letters were predicted based on surrounding letters. Example: T8, most likely E, not Q. Context helped fix unclear or smudged text. The diagram shows a blurred letter being interpreted by a language model. The model calculates probabilities and selects the most likely character. This transformed OCR into a context-aware system. Manual feature engineering. Before deep learning, OCR accuracy depended heavily on handcrafted features. Engineers manually defined what features matter. Hog, sift, Gabor filters were key extraction methods. Each method detected shapes, edges, or patterns differently. Researchers spent months designing single features. It was slow, complex, and required expert knowledge. Tesseract, 1984 to 1994, was the peak of traditional OCR. It combined many features into a robust system. The letter passes through modules labeled Hog, Sift, and Gabor filters. Each module extracts a different type of feature. Finally, everything is combined into a numerical feature vector. Deep learning changes everything. 2012 AlexNet beat all earlier techniques. Deep learning became the new standard. CNNs learned features directly from raw pixels. No more manual feature design required. Networks recognized edges, curves, loops automatically. Machines built their own understanding of characters, produced massive accuracy improvements. OCR became more flexible and powerful. The diagram shows the digit 8 passing through CNN layers. Each layer detects edges, strokes, and shapes. Finally, the network confidently predicts the final number. The architecture powering today's OCR engines. CNN extracts visual features from text. This replaces older handcrafted methods. RNN LSTM understands sequential letter patterns. It reads characters in context. CTC aligns predictions without bounding boxes, helps handle variable length text. Used in Tesseract 4.0, Paddle OCR, Easy OCR, standard in modern OCR engines. Hello flows from CNN to RNN to CTC. Each stage transforms the text line into a more accurate representation. CTC produces the final aligned reading. Self-attention powers next-gen OCR 2017 transformers introduce self-attention. AI could process entire images at once. Self-attention focuses on relevant parts of the text, helps with curved or long lines, great for complex layouts, perfect for multi-column or messy documents. Viantarakar became state-of-the-art, pure transformer OCR models. The attention diagram shows how the model looks at all image regions. It gives higher weight to important words like brown. This improves accuracy for complex text. Modern OCR systems understand layout plus meaning. AI now extracts structure, not just text. It understands tables, forms, and document layouts. Layout LM uses text plus visuals plus spatial positions. It knows how fields relate to each other. Donut outputs structured data directly. No need for intermediate transcription. The diagram shows John Doe being processed in 3 different ways: textual, visual, and spatial. This helps the model understand meaning, not just characters. OCR becomes automatic with vision language models. Models like GPT-4 Vision, Gemini, QuenVL read images naturally. OCR becomes just one small skill inside a bigger model. Specialized models like Mistral OCR and Paddle OCR VL exist. They extract structured text and layouts. DeepSeek OCR compresses long documents, helps process large files quickly. A handwritten recipe passes into a VLM and becomes a clean digital list. The AI performs reading, understanding, and formatting in one step. Challenges that still defeat modern OCR. Doctor handwriting varies heavily, hard for AI to decode. Historical documents have faded ink and damage. OCR struggles with clarity. Low-resource languages lack training data, makes recognition difficult. Adversarial text can fool AI. Small pixel changes trick models. True reasoning still limited. AI can extract text but struggles with deep meaning. 4 images show messy handwriting, old scripts, rare languages, and noisy text. These highlight cases where even advanced OCR fails. 5 profound truths. Simplicity is illusion. Reading is far harder than it looks. Progress is punctuated. Big jumps come from paradigm shifts. Goalposts keep moving. New challenges arise as old ones are solved. Context is everything. Meaning matters more than shapes. We're still learning. AI still lacks deep human-like understanding. Explosion of new document parsing models. Huge rise in models since 2025. The field is rapidly evolving. Examples: Monkey OCR, Minor U, Paddle OCR 3.0, DeepSeek OCR. Many cutting-edge systems. Industry and research growing fast. More reliable and flexible solutions. The timeline shows dozens of models released month by month in 2025. It reflects explosive research activity. The OCR trilemma: traditional pipelines brittle and error-prone. Complex rule chains break easily. General-purpose VLMs, accurate but slow. High GPU cost and latency. Hybrid approaches inherit limitations. Combining systems still causes issues. 2025 O strategy: commodity first, use Tesseract for simple tasks. VLMs for complex, use open-source VLMs for layouts. Hybrid CNR fallback. Go global, support multilingual models. Stay compliant, add human review. Transformative applications: visually impaired assistance, real-time text-to-speech. Legal and finance compliance, extract clauses and numbers. Healthcare digitization, convert handwritten medical notes. Archival preservation, digitize fragile manuscripts. Let's revise the full evolution of OCR, as shown in this final illustration. 1870s, 1950s, template matching. 1960s, 1980s, rule-based reading. 1974, Kurzweil breakthrough. 1990s, 2000s, statistical reading. 2010s, deep learning. 2017 present, transformers plus multimodal AI. Still unsolved, handwriting, ancient scripts, rare languages. The final illustration connects all eras. Mechanical systems, rule following, HMMs, CNNs, and transformers, showing the complete evolution in one image. And that's the amazing 150-year journey of OCR, from mechanical eyes to super intelligent AI. If you enjoyed this breakdown, make sure to like, share, and subscribe to GenAI Research Insight Hub. Thank you.